Good morning. I'd like to introduce myself and this part of your Foundations in AI study unit. My name is Vanessa Camilleri. I'm a lecturer at the Department of Artificial Intelligence at the Faculty of ICT, University of Malta. And basically, this tutorial will cover the topic of genetic algorithms. What you will be getting from this tutorial is the understanding of basic concepts and terminologies involved in genetic algorithms. We will also discuss some crossover and mutation operators, some selection methods, and other components. So what is genetic algorithm? A genetic algorithm is a search-based optimization technique based on the principles of genetics and natural selection. It is frequently used to find optimal or near-optimal solutions to difficult problems which would otherwise take a lifetime to solve. It is frequently used to solve optimization problems in research and in machine learning. So what is optimization? Optimization is the process of making something better. In any process, we have a set of inputs and a set of outputs, as shown in the following figure. Now, optimization refers to finding the values of inputs in such a way that we get the best output values. However, the definition of best varies from problem to problem. Yet, in mathematical terms, it refers to maximizing or minimizing one or more objective functions by varying the input parameters. The set of all possible solutions or values which the inputs can take make up the search space. In this search space lies a point or a set of points which gives the optimal solution. The aim of the optimization is to find that point or set of points in the search space. So what are GAs? Nature has always been a great source of inspiration to all mankind. Genetic algorithms are search-based algorithms based on the concepts of natural selection and genetics. GAs are a subset of a much larger branch of computation known as evolutionary computing. GAs were developed by John Holland and his students and colleagues at the University of Michigan, most notably David Goldberg, and has since been tried on various optimization problems with a high degree of success. In GAs, we have a pool or a population of possible solutions to the given problem. These solutions then undergo recombination and mutation, like in natural genetics, producing new children, and the process is repeated over various generations. Each individual or candidate solution is assigned a fitness value based on its objective function value, and the fitter individuals are given a higher chance to mate and yield more fit individuals. This is in line with the Darwinian theory of survival of the fittest. In this way, we keep evolving better individuals or solutions over generations till we reach a stopping criterion. Genetic algorithms are sufficiently randomized in nature, but they perform much better than random local search, in which we just try various random solutions, keeping track of the best so far, as they exploit historical information as well. So let's go to advantages of GAs. GAs have various advantages which have made them immensely popular. These are, first of all, they don't require any derivative information, which may not be available for many real-world problems. GAs are faster, they're more efficient as compared to traditional methods, have very good parallel capabilities, optimize both continuous and discrete functions and also multi-objective problems, provide a list of good solutions, not just one single solution, always get an answer to the problem, which gets better over time, and they're very useful when the search space is very large and there are large number of parameters involved. Limitations of GAs. Like any technique, GAs also suffer from a few limitations. So these include the fact that GAs are not suited for all problems, especially problems that are simple and for which derivative information is available. The fitness value is also calculated repeatedly, which might be computationally expensive for some problems. Being stochastic, there are no guarantees on the optimality or the quality of the solution. And if not implemented properly, the GA may not converge to the optimal solution. So why use GAs? GAs, genetic algorithms, have the ability to deliver a good enough solution fast enough. This makes genetic algorithms attractive for use in solving optimization problems. The reasons why GAs are needed are these. First of all, they're needed to solve difficult problems. In computer science, there is a large set of problems which are NP-hard. What this essentially means is that even the most powerful computing system takes a very long time, even years, to solve that problem. In such a scenario, GAs prove to be an efficient tool to provide a usable, near-optimal solution in a short amount of time. That's one motivation. The second motivation is the failure of gradient-based methods. Traditional calculus-based methods work by starting at a random point and by moving in the direction of the gradient till we reach the top of the hill. This technique is efficient and works very well for single-peaked objective functions like the cost function in linear regression. But in most real-world situations, we have a very complex problem called as landscapes, which are made of many peaks and many valleys, which cause such methods to fail, as they suffer from an inherent tendency of getting stuck at the local optima, as shown in this figure. So, another reason why we use GAs is that we need to get a good solution fast. Some difficult problems like the traveling salesman problem have real-world applications like pathfinding or VLSI design. Now imagine that you are using your GPS navigation system and it takes a few minutes or even a few hours to compute the optimal path from the source to destination. Delay in such real-world applications is not acceptable, and therefore a good enough solution which is delivered fast is what is required. Now move on to the next section in this tutorial, which introduces the basic terminology required to understand GAs. Some of the basic terminology. Before we begin a discussion on GAs, it is essential to be familiar with some of these basic terminologies that will be used throughout. The first is population. Population is a subset of all the possible solutions to be given to the given problem. The population for a GA is analogous to the population for human beings, except that instead of human beings, we have candidate solutions representing human beings. Chromosomes. A chromosome is one such solution to the given problem. Gene. A gene is one element position of a chromosome. Allele. It is the value of a gene a value that a gene takes for a particular chromosome. The genotype. The genotype is the population in the computation space. In the computation space, the solutions are represented in a way which can be easily understood and manipulated using a computing system. Phenotype. Phenotype is the population in the actual real-world solution space in which solutions are represented in a way in which they are represented in real-world solutions. Decoding and encoding. For simple problems, the phenotype and genotype spaces are the same. However, in most of the cases, the phenotype and genotype spaces are different. Decoding is a process of transforming a solution from the genotype to the phenotype space, while encoding is a process of transforming from the phenotype to the genotype space. Decoding should be fast as it is carried out repeatedly in a GA during the fitness value calculation. For example, consider the 0 to 1 knapsack problems. The phenotype space consists of solutions which just contain the item numbers of the items to be picked. However, in the genotype space, it can be represented as a binary string of length n, where n is the number of items. At 0 at position x represents the xth item that is picked, while a 1 represents the reverse. This is a case where a genotype and a phenotype spaces are different. You can see here in the figure the phenotype and the genotype space. The fitness function. A fitness function is simply defined as a function which takes the solution as input and produces the suitability of the solution as output. In some cases, the fitness function and the objective function may be the same, while in others it might be different based on the problem. Genetic operators. These alter the genetic composition of the offspring. These include crossover, mutation, selection, etc. We will cover these very shortly.